Good morning, everyone. Hi, Elijah. Good morning, Mr. Fosnight. Say hi to Harold. I'm Malachi. Cool to have you on board. Say hi to Harold. Well, I don't know how you guys are doing. We're getting along here in the Suriani household, watching a mama bird sitting on her eggs outside my window. Daddy bird brings her food once in a while, like a good daddy bird, and pretty soon there'll be little baby birds. But we've been talking about fiction. Has everybody gotten on to Google Classroom? If you have, let me know. If you have not, let me know. Just say yes or no. That'll help me kind of know where people are at. We basically have two things. We have blizzard packs, two different blizzard packs, one that we gave out when all this first happened, and the second one we gave out after the spring break. Okay, so there is work piling up there. So do get on there. Everything's set up. That's fine if you hadn't. Don't worry about due dates, even if it's past due. Just get on there and get that work done. If you have any questions, you can email me about it or go back and look at some of our videos. We basically are talking about Newton's 3 laws. Does anybody remember anything we talked about last couple about Newton's laws? There's Newton 1, Newton 2, and Newton 3. Newton's 3 laws can explain pretty much anything in the physics realm. And I know there's a few other people on. Feel free to say hi when you're here. There's 2 or 3 people that we haven't heard from. But let's talk about let's do a little review quickly. Talk about Newton's first law. The law, what we call the law of inertia, it's commonly referred to as the law of inertia. This is where I get to tell my really stupid jokes, my bad jokes. I used to call my old dog, used to call her inertia. Piece of space debris that is passing Earth sometime this week. It's about a mile wide. And we were talking about trajectories. And so if we have something's trajectory, let's say that this is the Earth, and this is a piece of space debris, and it's flying past Earth. Earth is going to act upon it. Okay, so this is an example of Newton's first law changing the trajectory of this piece of space debris. Normally, if there was nothing there, it would go by, keep going. However, let's assume this roll of duct tape is a planet like Earth. As this goes by, Earth's gravitational pull is actually acting upon it. Now, is it going to cause it to go like this? No. Is it going to cause it to change its trajectory a little bit? Probably. Instead of going straight up, it's going to go maybe be off a little bit. And so that is an outside force. That's one of the ways gravity works. We see gravity obviously working like that. a ball's just going to drop to the ground. But something that's in motion like this and is acted upon by something else, it will change its trajectory. How does something pass our planet hundreds of times and then eventually maybe become a meteor? At some point, its trajectory keeps on changing. So things do act upon the other thing that acts upon this, besides gravity, is basically what another thing we're talking about in physics is friction. Its resistance in air is an example of friction. Okay, that wind resistance, it's kind of like an imaginary sail or imaginary stop sign. It's going to slow it down a little bit, not much, and as it loses its speed or velocity, then gravity plays a stronger role and pulls it down. So reviewing Newton's first law, an object in motion tends to stay in motion unless acted upon by an outside force, like friction, like gravity, like wind resistance, which is the type of friction. An object at rest is going to stay at rest unless acted upon by an outside force. This thing is not going to move unless I decide it's going to move or something else acts upon it, right? So I could cause it to move. It can sit there, and it'll sit there for a long time. I've got a wheelbarrow out in the backyard. Guess what? That wheelbarrow isn't going to move until I decide to move it, or somebody else decides to move it. It's going to stay there, and it'll rust there, and it'll be there in 100 years if I left and came back and nobody touched it. It's going to stay wherever it is. This relates to why we wear seatbelts in cars. Let's talk about that real quick. We're driving in a car, and Joe is texting on his cell phone and decides to go through a red light, and you hit Joe. Car hits car, car stops. You keep moving unless you're restrained by a seatbelt. Even if you are restrained by a seatbelt, what keeps moving? Your head. That's why you end up getting whiplash. Or maybe your arms. Or maybe your cell phone into the windshield. Or maybe the person in the back seat. People in the front seat often get injured by people in the back seat who don't have their seat belts on. As a car hits something, if they have their seatbelt on in the front, sometimes the person in the back flies forward and injures them too. That's an object in motion tends to stay in motion. Okay, you want to keep going. The car wants to keep going. If something stops the car and you're the person in the car, you're gonna keep going, unless you have a seatbelt on. And we all know crash test dummies. Watch a couple of those videos and you'll understand Newton's first law, plain and simple. Now, number two, I posted a worksheet on Google Classroom about Newton's second law. Does anybody have any question about Newton's first law, or if they got online, Newton's second law of motion problems worksheet? Okay, basically, it is pretty simple math. We talked about this. Force equals mass times acceleration. That formula can be flipped around. It can be, depending on what piece of information you have. And I'll type that in there. Force equals mass times acceleration. I know how to spell. Okay, so that's in there. Whatever is on the left side of the equal sign is your unknown. And so you have to have two pieces of information. That's supposed to say mass, M-A-S-S. I don't know. And then the last one would be acceleration equals force divided by mass. Okay? Either one of those formulas, any eighth grader can do. You have the force, you have the acceleration, then you're looking for the mass. Okay? So the idea behind that is how much something weighs plays a significant role in how quickly it can accelerate, okay? And also how much force we're applying. Okay, this is a tablet. So here I have a tablet, okay? And here I have a little cell phone, okay? Their mass is different. If I apply the same exact force on these, and their mass is different, then the resulting acceleration is going to be different. That's a case where I would actually use that third formula, acceleration equals force divided by mass. Remember, we measure mass in newtons, different Newton scales, okay? There are others besides this, but I can actually measure. In this case, I'm measuring a pocket knife. It is a little bit over 1 Newton of force to lift this off the ground. So we can measure forces in newtons. Don't forget that. Okay. So if I apply 2 newtons on the cell phone, will it accelerate? And if I apply 2 newtons on this, will it accelerate? And so if we have the force, a consistent force, and we know the mass of an object, then we can determine its acceleration. If I know what its force is in newtons, morning, Brianna, and if we know what our force is and we know what our acceleration is, then we can determine the mass. And so whatever two pieces of information you have, what you don't have goes on the left side of the equal sign. Took the words right out of my mouth, Mr. Fosnight. So the assignment that you got that is in Google Classroom looks like this. It was posted last week, okay, where you have those formulas: force equals mass times acceleration, mass equals force time divided by acceleration, acceleration equals force divided by mass. If you want me to go over any of that, tell me now. And if not, we can move on. A couple more things. I did go over it the other day. Okay, so let's talk about Newton's third law. Well, the due date is actually, I think I actually put it in. If it wasn't today, it was Thursday. I would like you to try to meet those due dates, but you can still do an assignment late. At this point, I'm not going to take any credit off for you guys doing stuff late. Just get it done. You know, I'm not going to penalize you. Some of you are late to the game, but I'm not going to penalize you for turning something in late at this point. I'm happy that you have it done. Learning is a lifelong experience. I don't know what you guys have been doing with your time, gaming, but I've been doing all kinds of stuff here, and including last night, we tried to make suet, S-U-E-T, yeah, suet. If anybody knows what suet is, it is for feeding birds. And we actually took animal fat, melted it down, mixed in a whole bunch of bird seed and let it harden. And it came out okay for our first try. And we've learned a few things that by looking online at the way some other people did it, that'll help because it needs to be kind of hard. But that animal fat is good for the birds. They'll go in there and they'll peck at the seeds and they'll eat some of the. It's basically grease, and it's good for them, especially in the winter time. But at least I'll know how to do it for next time. Hopefully, you guys are keeping learning. Newton's first law, we just talked about. Newton's second law, it's called the law of force and motion, or the law of acceleration. Right, where you're basically using that formula that I just showed you. Newton's third law, for every action, there's an equal and opposite reaction. And I talked about this the other day too. You like my baseball bat? It's my grandson's. All right, so if I throw this ball in and it is hit with a ball, it's hit with the bat, the ball's going to go off in some direction, right? But it says for every action, there's an equal and opposite reaction. So if this ball's coming in, does that mean that this baseball bat is going to bounce back as a result of it? Probably not. I would imagine if somebody was, let's say Krabby was running down the hall and came around the corner and ran into Mrs. Yingling, they would both go bouncing off of each other in a somewhat opposite direction. One would probably take the brunt of the force more than the other. And the rest of us would be laughing as long as nobody got hurt. But if you think about this ball's coming in and you're hitting it, it's doing something to the momentum of this bat. It may be slowing it down. Maybe it's changing the direction of the bat a little bit. But there is a reaction. Now, if this was a bowling ball and I threw a bowling ball in at this plastic wiffle bat, it certainly would send this in the other direction or down, or might even destroy it. Who knows? This might get destroyed with a bat. So sometimes we don't see reactions, but they exist. Every time you drop something, it's the same force, Newton's third. Every time there's an action, for every action, there's an equal and opposite reaction. So if we drop a wiffle ball on the ground, are they reacting to each other? Mm-hmm. Are you able to measure the earth reacting to being hit by this ball? Heck no, it's way too small, too minuscule. What if the earth got hit by a large space object that weighed millions of tons? What would the reaction be? It would probably change the orbit that we have around the sun. So anytime there's an action, for every action, there's an equal and opposite reaction. So I do have an assignment that goes along with this. And it basically gives you examples. And there's going to be two parts to it. Number one, you have to come up with your own examples of an action, what the action is, the action for what we call an action force and reaction force. The action force is what causes something. What is the reaction force? Let's say that we, again, I'll say I throw this ball. The action force is the ball coming in. The reaction force, bat hitting the ball, sending it back out. Those are examples. You have to come up with your own example that you can think of to include on the Google Doc that you're going to be sent. Does anybody? So for let me give you one example. A diver, I'll read off of here. A diver dives off a raft. What happens to the diver? What happens to the raft? Okay, and so in this case, when he dives off that raft, the action force is his diving off the raft. What is he doing when he's diving? He's actually bending his legs and springing, right? And so it's pushing his body upwards. It's also pushing the raft down or back. So does the raft remain in the exact same position? Probably not. So that's the reaction force, right? The action force is his bending down to dive. The reaction force is that raft, by him pushing against it, gets pushed out of the way. That's what happens when you're in the water, right? Or in the air. When you're in a fluid, it's super, super obvious. Okay. So hopefully you understand that. There are only eight questions on this action reaction sheet. Basically, it's saying, okay, what is the action? What is the reaction? If I hit a ball with a bat, that's the action. What's the reaction? Ball goes to out in the field somewhere, or into somebody's glove, or depending on how I hit it. Okay, we're about out of time. I hope you guys make sure. I'm glad to see a lot more of you guys joining us. Make sure you are sharing your data when you turn something in. Make sure you're actually submitting it, and not just doing the work and let it sit there. Number one. Number two, make sure your Google Docs are shared with me. They should be automatically, but if you create your own for some reason, make sure you share it with me. Don't hesitate to call me. If you have any questions, say goodbye to Harold. And that's about it for the moment. And thank you for joining. I appreciate you 8th graders coming alive and getting out of bed before noon. I think language arts is starting in a minute, so I'm going to get off of here. Hope you guys have a great day, and we'll see you later in the week.